This is the last question on the homework from 6-1. It's stupid. So I'll talk about how we do this, because this is, you hear me saying I'm getting really tired of saying it, and you're probably getting really tired of hearing it, but this is an end of course exam type question. Okay, so I want to make sure that we're able to kind of navigate these types of things. It says at a local fitness center, members pay $12 membership fee and $5 then for each aerobics class. Non-members pay $6 for each aerobics class. Okay, do non-members pay a membership fee? No, because they're non-members, right? It says for what number of aerobics classes will the cost of members and non-members be the same? So when we look at this, there's two relationships, and I've highlighted them. We've got the green relationship being a member and the cost that's going to require for a member, and then the blue one is the cost for non-members. Remember, we're talking about two things here. There's a cost that is being dictated by the number of classes I take, right? So I'm going to let my Y value be the cost, and I'll let my X value be the number of aerobics classes taken. Does that make sense? Because the more aerobics classes I take, the more the cost is going to be, right? So we can see which one's supposed to be the independent, which one's supposed to be the dependent based off of knowing that the cost is going to rise based on how many classes you take. So let's look at the green one here, okay? If my cost is going to be dependent on how many classes I take, if I take no classes as a member, what is my cost that I have to pay to this place? $12, okay? You have to be a member, right? Now, that's what this is saying. You become a member, but then you get lazy and don't take any classes, okay? But if I take one class, how much extra money am I going to pay? $5, right? But if I take two classes, that 5 would actually be, just careful, it'd be 10, wouldn't it? Yeah. Okay, if I take 3 classes, that 5 would be 15, right? 4 classes would be 20. What is allowing me to change the 5 to a 10 to a 15 to a 20? It's X, right? Okay, so when X is 1, I'm going to pay the 5. When X is 2, I'm going to pay that 10. When X is 3, I'm going to pay 15, right? So there's the equation that we're going to set up for members and the cost that members are going to pay. Now I've got to do the cost for non-members, okay? So if I'm a non-member and I take no classes, how much is that going to cost me? $0. So where it says plus 12 in the other ones, this one's going to say plus 0, right? And we don't write that, so nothing yet. Now I get to the fact that it's $6 for every class. Well, if it's $6 for every class, that's the same idea. That's going to be 6 for one class. It'd be 12 for 2 classes. Be 18 for 3, right? What's allowing that 6 to go to 12 to go to 18? Yes, right? It's when X is 1, that's one class. When X is 2, that's 12. When X is 3, it's 18, right? So those are my two equations that we're going to be asked to create. Now the question is, when or for what number of aerobics classes will the cost be the same? So that's a way of basically saying, in a contextual problem, when you graph these two lines, where do they cross? Okay? So look for that ordered pair of where they cross. Now, we can do this graphically, and I want to come back and show you that, yes, we can do it graphically, and this was part of 6.1, but from what we've learned in 6.2, it should be actually a lot faster to graph or to solve this without a graph. Okay? So 6.1 says, we'll pull up a graph here. Let's see. I want to show you guys the calculator that I did some, I don't know if I told you this yesterday, did some further investigation on, I did tell you this? Okay. Yeah. So, like Desmos, this is going to be what's going to be on your test when you're able to take this. So, when we have access to this, we can just type in y equals 6x, or I guess it was 5x, right? 5x plus 12. That was one equation, right? The other one was y equals 6x. There's my other one. Okay. Now, as we scroll up here to see where they cross, to find the place that they cross, I just need to click on those lines and then highlight that point. So 12, comma 72 is where they cross. Does that make sense? So 1272 is their point of intersection. Let's talk about what that means. 1272, and this is what I think gets lost sometimes when we're in a class, a math class, and it's essentially because I think it's been kind of beaten into you or just ingrained in the process that we go through, like from third grade to now, is that we're usually looking for the answer, right? Once we get the numbers, we're done. But we're starting to see now situations that not only are interested in the numbers, but what do the numbers tell us? So when I look at 12, 72, that's the answer. But what do those numbers mean? Well, remember, 12 is a x value, right? 72 is a y value. If I come over here, 12 must be the number of aerobics classes. Does that make sense? And then the 72, that must be the cost then when we take 12 aerobics classes. Does everybody kind of understand that? And that's if I plug in 12 for both those equations, 5 times 12 is 60, plus 12 is 72, right? 6 times 12 is 72 as well. So that's the point in which we reach we call it an equilibrium in regards to our y value is the same based on that x value. Okay? So if I take 12 classes, doesn't matter how you pay for it. You want to be a member or non-member, it's going to cost you the same thing. But around 12, or before 12, say before 12, before I take 12 classes, let's look at that picture again. Okay, so like this point, like right here where my cursor is. Actually, let's go to like right there. Where my cursor is, that's taking 2 classes. Okay, we see it's on the x-axis would be on the second block there, and I think it's going by 1 there. So be 1 class, or sorry, 2 classes is going to be cost me what, $22? Does that make sense? Okay. So for the red equation, which was 5x plus 12, okay, it cost me $22. As a member, $22 to be taking 2 aerobics classes. If I look at the blue one down here, the blue one is at a y value of 12, right? So for a blue one, if I'm only going to take 2 aerobics classes, the blue one says you're only going to pay $12. Okay, so which one's cheaper? $22 or $12? It's 12. So if I know I'm only going to take 2 aerobics classes, then I probably shouldn't become a member, right? Does that make sense? So before 12 months, before 12 aerobics classes, it makes sense not to be a member. But let's say that you know you're going to take more than 12 classes. I'm going to take more than 12 classes. Okay, like maybe at this point right here, I don't know what. Okay, so that's, let's say my cursor right here is at, like right there is at 18 on the x-axis. Okay, if I'm going to take 18 classes, now we see that at that point where my cursor is, that blue point is going to cost me $108, and right here for 18 classes as a member, it's going to cost me $102. Does that make sense? Okay, so at that situation, after taking 12 classes, it makes more sense to become a member because now you're going to be saving yourself money in the long run. That kind of makes sense? So what we like to do is we like to find a place that they're equal, because then if we know where they're equal, everywhere else they're unequal, and I can make decisions then on what would be best for me as a consumer. Now, we did that graphically. Let's do this. We know from what we've learned so far in 6.2, is that y right there the same as that y right there? So that means this here is the same as that, right? So can I take 6x equals 5x plus 12? Subtract 5x. Does x equal 12? Which is exactly what we found graphically, right? When I want to find y, I'm probably going to plug that in right there. 6 times 12 is 72, right? So the hope is that, yes, the graph works, but I would think that knowing what we know from 6.2 with substitution, you can actually get to your answer much quicker because you don't have to go to your calculator, graph it, or go to a piece of paper and graph things and see where they cross. You can do the algebra. Questions on that one? Boston, does that suck less than it did before? Okay. So yesterday, there was a case that in the middle there that we talked about. I want to talk about these next two special cases. So go ahead and get your worksheet or get your handout out. Sorry. Eating a piece of candy and it won't dissolve.
Yeah, what?
What?
What is it? Now,
Cookie Pop.
you dropped it, you nasty.
Want some?
I wish there was a kid
No.
sitting there so I could jump
Huh? No, I don't know. We're probably going to spend a little bit more time on 6. I know today we'll spend more time on 6.2. We might even spend tomorrow on 6.2.
I know it's not like hard, right? What the?
I'm hungry. Can I just stop?
What's not good? Like sometimes like
complain
about instead of like an x upon there would be like a negative 3x plus like negative x plus 6 equals.
So let's do this example. We're going to do a handful of examples and see if me knowing that now, I'll see if I can slow things down. Talk about your choices then for how to substitute. I think that's maybe the question there. And if I don't answer your question, if it's still confusing afterwards, let me know. We'll talk about it. So we got two special cases here that I want to make sure we talk about because they're actually simple cases, they're simple situations, but I think we talked about it in that middle one yesterday. Sometimes with simplicity, we overthink things and it actually becomes harder. We come to like what we think might be a roadblock and we're not sure what to do. Okay? So I want to make sure we see at least one example of both these. And this one here is a situation where they are telling you what one of your coordinates is for your ordered pair. Okay? So as we've always done, we're going to look at these and say, okay, is in one of these equations, is there a variable already solved for? Meaning, do I have a 1x or a 1y all by itself already?
Yeah.
Yeah, that's in that bottom one, right?
I did this already.
Okay. Now, most often, and in all the examples we've seen so far, that thing I just highlighted has like an x plus 3 over here instead of the 1. Or like a 2x plus 5 or whatever. There's some expression. Here there's no expression other than that number, right? So it is telling you what y is. When you're done, your y value is going to be 1. Does that make sense?
Yeah.
Okay. So the idea of this being so simple that sometimes we struggle with it is now, well, what do I do with that y equals 1?
You plug it into y, duh.
Yeah, plug in for that y. So here's one thing that I talked about this in the last class, and I think it helps people understand what to do. When you take an equation and you're going to solve it for y, like we've got that bottom one solved for y, and you mess with that equation or whatever, what you do next is plug that into the equation that you have not touched yet, okay? So we get y equals 1. I'm going to plug that into the equation up top that I haven't dealt with yet. Does that make sense to everybody? Okay? So when I plug that in up there, I'm going to get 2x plus 1 equals 3. Subtract 1 from both sides, and divide both sides by 2. So we get 1 comma 1.
Tell me why I do those easier than the actual problems themselves. Like normal problems, multiplication. Tell me why I do those better than, like this better than those.
It might be depending on what you're choosing as your variable that you solve for. So let's kind of do this one maybe again in a different way, because some people might see this. If I look at like 2x plus y equals 3, can I rewrite that as y equals 3 minus 2x? Does that make sense? The bottom one is still y equals 1, right? Let's not touch that. So somebody in the last class asked, well, I thought we had to put them in both equals y equals and x plus b form. You don't have to. I think this demonstrates that you don't have to. But here, they put them both in the y equals and x plus b form. So if those two things are the same, what's that tell me about those two things? They're the same. So then I go 3 minus 2x equals 1. Subtract 3 from both sides. Divide both sides by negative 2. I still get x to be 1, right? So the idea is when we do these in class, you might, the way we do it, I want you to understand it's not the only way. There's 2, 3, 4 other ways you could do it. So just because that's the way that I'm driving the question or I'm trying to learn this to see the problem doesn't mean that's how you have to abide by it in your homework. What you do have to abide by, though, is the principles. You have to first decide what variable you want to solve for in one of those two equations. Then do that. And once you have that, then take that and substitute it into the equation that you have not touched yet, and then evaluate that. Does that kind of make sense? So as long as you do those processes or those principles, you should be okay. Okay. Now, somebody in the last class, like I said, I thought we always had to have y equals mx plus b for both of them. You can. Okay, but let's go back up to this example 5 here. I'm just going to write it on the side. It was y equals x plus 3, and I think it was 3x plus 4y equals 7. We solved that yesterday by saying, well, in that top equation, y is already solved for, right? So right there, I know y is x plus 3. So if you look at the work we did, we came down here, and we replaced it, and we got 3x plus 4 times x plus 3 equals 7, right? Remember doing that yesterday? So we did that, we solved it, and all that kind of stuff, okay? Here's the argument that we made in the last class. This top one is already in y equals mx plus b form, right? Can I put this one in y equals mx plus b form? Can I subtract 3x from both sides? Yeah. So we get 4y equals 7 minus 3x. Can I then divide both sides by 4? So you get y equals 7 over 4 minus 3/4 x. That is the first equation, and this is the second equation. Just that second one's been adjusted a little bit, right? Now, why don't we like usually that second equation? Because there's fractions, okay? And if you're not going to pay attention to those convenient substitutions, the simplest substitutions, like replacing y in that second equation with x plus 3, then you're inevitably going to come across fractions by doing this. However, this for some people might make more sense because now is that y and that y the same? So then doesn't it make that and that the same? Okay, so let's go ahead and put those two things together. So x plus 3 equals, now 7/4 minus 3/4 times x. What can I multiply everything by here so that the denominators go away? 4, right? And that's the thing. Like, even though we do get fractions, I think in every one of these we do, you'll be able to get rid of those fractions in the equation just by multiplying, in this case by 4 or whatever it tends to be in the other problems. So it should be one extra step of just multiplying everything by 4. So 4 times x becomes 4x. 4 times 3 becomes 12. 4 times 7/4 just gives me 7, right? 4 times negative 3/4 just gives me negative 3. And I get that, right? Now here's my question. I'm not going to go any further with that, but let's see real quick if that is the same thing as this. If I distribute, I get 3x plus 4x plus 12 equals 7, right? If I take this 3x right there to the other side, does it give me 4x plus 12 equals 7 minus 3x? Does that make sense? Is that right there the same thing I got in that box? Yeah, so as I continue either of those down further and solve for x, I will get the same answer, right? Okay, so I guess the demonstration here is as long as you make a legal substitution, okay, you replace something with what it's equal to so that you get rid of a variable, you're going to generate some algebra. As long as you conduct the remaining steps correctly algebraically, you're going to get the answer. What I'm saying then is that your neighbor might do it completely different than you, and you get the answer. You might come to me and ask me a question, and the way I see it, and the way I ask you to kind of work with me on it, might be completely different than what makes sense to you. Does that make sense? Okay? But regardless, our overall principles are going to be solve for a variable, replace that in another equation, and then solve for the variable that's left over. Okay? Let's do this last one here on the handout. The y equals x. Okay? If I look at that, is that variable already solved for? Which variable is being solved for there?
Both of them.
Both of them. Okay? Both of them are isolated, and both of them have a 1 in front of them, and that's what we meant by solving for, right? We isolate a variable and get a 1 in front of it. Okay? And that happens on both sides here. So that's nice. Okay? So what that means to me is that I don't need to adjust this at all, but what it means is that when I come down here to the bottom equation, wherever I see a y, what should I replace it with? X. So I get 2x plus 1 is equal to x, right? So then I'm going to subtract 2x from both sides. And I get 1 is equal to,
-2x.
Careful.
Oh.
1x minus 2x is negative 1x, right? So then I want to multiply both sides by negative 1. And I get that, right? Okay. All right, you can divide too. So I want my negative 1x to become positive 1x, right? So multiplying by a negative 1 is the same thing as dividing by a negative 1 because of the fact that 1 is your multiplicative identity. Okay. Multiplicative. Weird. So now, let's go back and plug in. I can plug in, based on what we talked about, into that equation or into that one. Which one would be the best to plug back into? That top one. Because it says, if you know what x is, y is x. So if x is negative 1, so is y. And that's what I want us to make sure we understand in that problem. Okay? Now, if you were a person that says, I didn't see it that way, what I did was, if y is x, that means everywhere I see x, I could replace it with what? Y. And if I have 2y plus 1 equals y, subtract 2y from both sides, you get 1 equals negative y. So then positive y would be negative 1, right? So it would give me that number first. And then when I substitute back in here, that's going to give me my x value of negative 1. Does that make sense? You can substitute as you see fit. You can even do it in that bottom one. Okay? Let's just do this in the bottom one here. If I've got, let's skip it and go to a different problem here. Because it's really, when we substitute using this bottom one, it's not going to generate anything algebraically that looks different. What's this? I'll give you a practice one here, and you guys take a minute to sift through it, and then we'll talk. So let's go with, All right, let's go 3x plus 4y equals 6. And then 2x minus y equals negative 7. Why do you hate these? When we look at this, neither the x or the y in the top equation is a 1x or a 1y, right? The bottom equation, we don't have a positive 1x or a positive 1y, but we do have a negative 1y, right? Okay? So what we're looking for, if we're going to substitute efficiently, is the variable that either has a positive 1 or a negative 1 as a coefficient. Because if it is a negative 1, we can quickly change it through multiplication of negative 1 to a positive y. Okay, or positive 1y. So what I'm going to do is I'm going to take that bottom one. Okay? And I'm going to try to solve that bottom one for y. Okay? Now you got options, and I don't care how you do it. What makes sense to you? Do you guys want to think about it this way? If I add y to both sides, will that make my y positive? Yeah. Okay, so you can do that. I think most people, maybe a lot of you would like that. Could I subtract 2x from both sides? And that would leave me with a negative y, right? Okay, so let's go ahead and let's add y to both sides first. Let's do this both routes. If I add y to both sides first, I get 2x on the left-hand side, and then negative 7 plus y, right? So now what are you going to do to solve for y? Okay, here's the thing. You can divide by 2. Hold on. Let me answer. You can divide by 2, but what would you be isolating? You'd be solving for x. Nothing wrong with it, but then when you go back into the other equation, you got to replace x then. Does that make sense? Okay, so we're just trying to get. I want to solve for this variable here because then I don't have any fractions, right? If I divide everything by 2, I'm going to have 7 halves and 1 half y. That might be messy. Okay, but if I add 7 to both sides, do I get y to be 2x plus 7? Does that make sense? Because remember my goal was to solve for y. So when we say solve for y, it means y by itself with a coefficient of 1. And that's what we've got going on here. Okay? Now, if you went a different route, if you left this y where it's at, and I know it's kind of maybe how we did things early on in the year, if I'm going to solve for that variable, I'm going to leave it where it's at. So what needs to get separated? What needs to go away on that side? The 2x, right? How do I get that 2x to the other side of the equation? Subtract it, right? So I get negative y is equal to negative 7 minus 2x, right? What do we like this thing to be? This negative y, we like it to be positive y, right? What could I multiply by so I don't change the amount, but I change only the sign? Okay, if I multiply by 1, it's not going to change anything, right? Well, if I divide by 1, it's not going to change anything, right? Multiplying or dividing by 1 keeps it the same, right? Okay? But if I multiply by a negative 1, what's a negative times a negative? Positive. So is that going to change that to a positive y? Yeah. If I multiply negative 7 by a negative 1, what's that going to change it to? Positive 7. And I multiply negative 1 or negative 2x by a negative 1, it changes to positive 2x. Is that there the same thing as that there? Yeah, just things are jockeyed around with addition, but that's okay. Okay, we got the commutative property of addition. Does that make sense? And I think just talking to some of you, you're struggling with especially when it's a minus. If it was just a 1y there, a positive 1y with this, would this have been a lot easier question? If this is plus y, all you got to do is remove that 2x over and you're good to go, right? Okay? But if it's negative y, you need to, algebraically, it's multiplying everything by a negative, but if you want to, if you just want to remember, okay, well, if it's negative y, let's change that sign. So then I got to go through everything else and change everything else to sign as well, to the opposite. So now, we did all that preliminary work so that we could say, well, if y is that, can we, now I have not touched this equation yet, right? Have not touched that. So once I solve for y, now I'm going to take that solved y and plug it into the equation that we haven't touched, right? So does it make sense that that's going to generate 3x plus 4, but now y becomes my 7 plus 2x? And I got my 6. Does that make sense? So I'm taking this amount right here, and I'm rewriting that y as that amount. Questions on that? What's next step? Distribute, so I get 3x plus 28 plus 8x equals 6. 3x plus 8x is 11x's, plus 28 is equal to 6. Subtract 28 from both sides. What's 6? So 11x equals negative 22. X then is equal to negative 2. Okay. Now if x is negative 2, plug that back in. So now here's the thing. You can plug back into any equation that you have either started with, like that one, or any equation that you generated throughout the entire problem. So that one, right? Does it make, because I'm trying to solve for y, does it make sense to put it into this bottom one? Because y is already solved for there. Okay? But you can go into any one, as long as it's got x and y in it, you can plug into any of them. So when I plug this into that one, I get y equals 7 plus then 2 times negative 2, and that's 7 minus 4, which ends up being 3, right? So the ordered pair x was negative 2, y was 3, and there is our solution. Now here's the thing. Would you guys agree that's probably maybe one of the longer problems you've ever done? Okay. If I make a sign mistake early on, is that going to ruin everything? Yeah. If I make a multiplication mistake early on, it's going to ruin everything, right? Okay. I heard somebody say, oh, it's minus 28. Did somebody add 28 to both sides?
That was me.
Okay. So you did everything right, correct? You did the process right.
No, I didn't.
But one small error of adding instead of subtracting from both sides negates all this correct work before that. Because when I take the x here of negative 2, right? Plug it back into this equation that said y equals 7 plus 2x. So that x becomes 2, right? So it's 7. Okay, that x becomes negative 2. So it's 7 plus 2 times negative 2. So that's going to become negative 4, right? So 7 plus negative 4 is something like 7 minus 4. And there's my 3. Do we feel like we're maybe getting better at this? Okay, so here's the thing. That system of equations, after we talk about section 6.3, I don't think anybody is going to solve that system using the technique I just showed you. Okay? Because in section 6.3, we learn that there's an easier way. Okay? And that's kind of where that's going to kind of take us. But the idea is that after we get done with section 6.3, is that we can look at any set of systems of equations, and now each one of those, we might have 3-4 different ways of solving it, 3 different processes for solving it, and we're just going to have to do a little bit of forecast. Okay, does this one is going to provide less work with maybe process 1, graphing, or maybe less work with solving using substitution, or maybe does it less work solving using what we call elimination that we're going to talk about in 6.3. It allows us that for any system we come across, we have a varying amount of tools that we can maybe adequately address each equation or each system differently. Does that make sense? But if I wanted to dig a hole, okay, and I go to my shed and I've got a shovel, a post hole digger, and a spoon, is the spoon going to be adequate for digging a hole? Probably not. Will it do the job? Yeah, okay. So substitution might not be really appropriate for a question, but it'll get the job done. Does that make sense? It's going to take me time, okay? Where, the post hole digger or the shovel, probably the shovel, depending on the size of the hole I want to make, is probably the best route. Does that make sense? So that's kind of what's going on here when we're learning various ways of doing these problems, okay? I'm going to give you guys a homework assignment. This is not going to be due till Monday, but I want to make sure that you keep this handout because there's 30 questions on it. You're not going to do all 30 of them, but we might use this for a couple different assignments. So don't lose this handout. So what I want you guys to do right now is for Monday, questions 5 through 12. Okay? So the first 6 of those, they're all in y equals mx plus b form, right? Okay, 5 through 12. And then 11 and 12 are you having to decide how to substitute. And I think they should be, hopefully 5 through 12, they're the simpler cases. So I'll make sure we can do those. And then maybe tomorrow's class, I might add a few more to this that I want you to complete for Monday. But that gives you something to start on maybe this evening, not couple those out. Yes.